Hello. I don't see anyone else who has joined in, so let's wait. I see that Sarang says Druhi are trying to join. So let's wait for a minute, then we can give it a start. Uh, see Sarang's now, so maybe I can start sharing my screen. Hi Sarang, hi Rohi.
Hi, Bhamik.
Hello,
Hello.
hello. I hope you both can hear me as well as you can see my screen as well. So let's try to start from where we left off yesterday. Because of time constraint, we could not really finish the discussion. So what we were doing is we were trying to solve answer one. Then we will solve answer two and answer three. The answers or approaches to all of these questions will be different. Okay, and I'm going to explain in each and every case why they are different, what kind of way we are using, what other alternatives do we have, and so on. Right. So let's start with the first one, which we were doing yesterday. So just to repeat the question, we have breakfast cereal standard boxes. Company claims 295 gram is the average weight, with a standard deviation of only 25 gram. Sometimes the question will tell us explicitly that it is a normal distribution, but in this case, let's say, okay, let's for the sake of this formula and use of that formula, we have proactively admitted that this is a normal distribution. Okay, basis which we are trying to answer three questions. Question number one: what is the probability that a standard box, if I pick any box in the supermarket, it is going to weigh or it's going to have items inside the box which weighs less than 280 grams, right? So for that, we already know what is the formula for Z. We have a formula for Z, which is x minus sigma divided by x minus mu divided by sigma. And that's exactly what we have done over here. We have taken x, which is r 0.28, which is my random variable in this case, right? Then I'm subtracting the mean from that random variable, and then I'm actually dividing it by the standard deviation. Now it is obvious that this answer is going to be negative, right? It is obvious because I know that if I have the normal distribution, which is something like this, and I have a mean, which is something like this, and I have my random variable, which is here, right? My random variable is here. My mu is here, and I have some kind of a standard deviation, which I have already calculated. So it is quite obvious that because my growth progression, as I told you, is on this side or in this direction, then anything which is going on this direction than the mu or as compared to the mean is going to be a minus. So that's why this z value is actually minus in this case. Clear cut. Now the question here is, if this z value is minus, what do we do? If this z value is going to come, let's say tomorrow I do some other test and the z value comes 1.2, what are we going to do? What if my new x is over here? Let's say this is x1, a random variable in question 1, and x2 is a random variable in question 2, which is going to be the case. As you can see over here, 350 grams is going to be the second random variable, and my mu is what? My mean is 0.295, right? So 350 is actually greater than 295, so it will come on this side of the graph, so it will fall somewhere here, let's say, right? So the value is going to fall somewhere over here. This is the value. This is not the value, by the way. Yeah, this is the probability density graph. So the expression here is not what is x2. I just drew it so that I can mean that x2 falls on this line. So this line is actually perpendicular to the x-axis. And then at this point in time, we have got the next random variable, which is more. If the random variable is more than mu, then obviously this calculation that I have over here, as you can see in the formula bar, this is my random variable. I am subtracting the mean. Then I am dividing the entire thing inside a bracket I've used. Inside a bracket, these things are, and then I'm dividing it by the uh, standard deviation. Then it is obviously going to be a positive number. If it is going to be a positive number, how am I going to deal with that? Right? Is what is going to be my question. So Basis what I'm trying to look. Even if you look at the third question is going to be kind of a range based question. So all of these three questions are actually different in nature, and we are going to use that z value in a different ways to solve the problem. Okay, so the formulas that we are going to use in this case are going to change. Okay, but the intuition remains the same. I somehow get hold of the z value because I have mu and because I have the standard deviation. So I'm very lucky that I have both the mean and the standard deviation. In some cases, if you look at the problem statement or when you work on some problem, you may well find that there is some research which is already done, in which case you are already provided with the z value and maybe with the mean, right? You are provided with the mean or with the standard deviation, either of them, and you are provided with the z value. So simply you can put it into this formula and then you can find out the unknown. So once you have the unknown, you can find out the probability, right? So that's the approach that we are going to overall use. Let me clear the drawings. Let me go back to this formula now. So you have seen this formula. This is easy because we have already looked into it. What about this formula? This formula is something that I would like to quickly describe over here because I know it is going to be confusing for the first time. Let me put this in bold. Norm dot dist. So this is what we are trying to figure out. This is a normal distribution. You have already assumed it is a normal distribution. So in Excel we have a function. We have a formula which is known as norm dot dist. Norm dot dist is going to take 4 parameters. Okay. The parameter number 1 is going to be my x or my random variable. Okay. The second parameter is going to be my mu or my mean. The third parameter is going to be my standard deviation. And the fourth parameter is a Boolean value, 1 or 0. The fourth parameter is the most important in this case. Why? Because it is a decision making. Everything else in this formula, as you can see, the random variable, the mu, the ST is basically a number. If you have taken a sample, you can calculate them. That's not an issue. And the random variable is going to depend on your question. So putting these three values is not a problem. The problem comes over here. Should I put 1? Should I put 0? If you look at the help of this formula, it will tell you whether your graph, let's say I have a distribution again, I'm going to draw a quick, let's say, distribution. If a distribution is going to, let's say, look like this, although there is no point of drawing this y-axis, maybe from next time I'm going to skip that. So if you have a distribution which looks like this, right? Is this value going to be 1 or 0? In case of a normal distribution, ideal condition, or majority of the cases, it is always 1. Why is that the case? Is because when I'm taking any real numbered value, the growth is on this side. The values are increasing as I go along. So this value is less than this value is less than this value, and so on and so on. What I mean by that is, at any point in time, if I draw a line, let's say this is my a random variable x1, and this is my mean, which is mu. If I'm drawing a line x1 and I want to know what is the probability less than this point, or what is the probability of occurrence of x which is less than x1, similar to my question number 1, right? What is the probability that standard box weighs less than this value? If I say less than this value, I'm looking at an area under the curve which is until x1. Until x1, not equal to x1, until x1. It is clearly saying it is less than. That's why it is until. It is not inclusive. That's why, as you can see clearly, you can understand, the moment I select different random variables, I am taking a cumulative area under the curve, right? I'm taking the entire area under the curve, which seems like a cumulative one, because tomorrow if I have another variable which is like here, which is, let's say, x2, then I can simply say this is this much part, or I can say this is part 1 and a summation of, let's say, part 2. So part 1 and part 2, I can simply take both the probabilities, simply apply the addition rule, and then I can get the probability of getting a value until x2. Until x2, let's say this is not the question number 2. Okay, question number 2 says more than x2. So I'm saying if I'm taking until x2, then I can consider cumulative value, right? What happens if I am looking at something which is non-cumulative? Non-cumulative in the sense it is in the growth direction. So what I mean by that is, let's say I have this distribution here, and I have the mean over here. I am trying to take a value. Let me draw the x-axis as well. So this is my mu. I'm trying to take a value which is something like this. This is going to be my question number 2. So let's say this is x2. Now x2 is something which is greater than mu. If that is the case, then what do I do? If that is the case, this is no longer cumulative because now the area under the curve that I'm looking for is on the other side. I'm not looking on the direction of the progression. And that's why in that case, the value is going to become 0. That's exactly what we are going to do over here. Or there is one more formula that we can make use of, right? If I put this into the formula, see what I've done. The first value is the random variable, right? So I have put the random variable here. Then I have put the mean. Then I have put the standard deviation. Then I know this is the cumulative case, right? So that is why the value of flag is equal to 1. You can also put true and false. Okay, it is not a problem. Instead of 1 and 0, it is easy for me to understand Boolean in terms of 1 and 0 because of my programming background. But if you are okay with using true and false, that's also fine because this function is going to support both. There is no problem. You can replace 1 with true and 0 with false, not an issue. Once I put over here, I get a number. Okay, this is my answer. I simply take this number and multiply this number with 100. Okay, then I can simply represent the probability in terms of percentages. So what I can say, I can simply take this value and I can say equal to this value multiplied by 100 is the probability that I'm looking for. Maybe I can also do something fancy. I'm going to round the value to 2 places of, let's say, decimal, and I'm going to say 27.43 is the probability or the percentage, okay, or the chance. So there is 27.43% chance that the standard box that I have picked from the shopping mall is less than 280 kg. Now this depends on the business context if this is really a problem or not. It may or may not be a problem. However, it does not prove the opposite. Always remember, you do not prove the opposite using this. This is okay, this is a probability value, but this is not a case or a scenario where you prove the opposite as well. What I mean by that is, let's say I am going to take 1 minus this. So 1 minus this, 1 minus C11 is this. How is this? No, sorry, I should have taken 1 minus this. I've done a mistake. Okay, 1 minus this is this 72.575. Let me just convert this one into, let's say, round this multiplied by 100 to 2 places. The reason why I did this is because just to tell you that just because there is a 27.43% chance that a standard box weighs less than 280 gram, that does not mean there is a 73% chance that it is going to weigh more than 280 grams. The opposite is not what we have proved. Why? Because this opposite is not for which we have calculated the z value. We have calculated the z value only for one direction. Or in this case, we have calculated the z value for a cumulative nature inside the normal distribution. Please do remember this. The minus is not going to be the same. Okay, in some rare to rare cases, this might come out to be equal, but that's not what we are supposed to do. This is wrong. We should not be doing this. We should only be doing what we are asked to do, or what is the question we are trying to answer. We know that this is really contradictory with the definition of the probability, right? Because in probability, what do I know? The probability theorem clearly states that if I have, let's say, a coin toss, the probability of head is 0.5, then the probability of tail is going to be 0.5. Why? Because summation of all the probabilities is going to equal to 1. In this case, that may be the case. Why? Because I'm taking the probability out of a density function and I'm calculating it by means of the score, which in this case is the z value. The z value is irrespective of the scale of the variable. So it is not always true. I'm not saying it is false. It is not always true that the opposite is 72.57. The opposite may not be. Okay, there will be cases or impact of confounding variables, in which case that's not going to be true. So let's not look into that. If we are asked, then we will look into that. Else we won't look into that. Okay, maybe we can take that as question number 4. Now let's look into question number 2. So I'll say answer 2. Let me just zoom out a little bit because I don't think I'll have space. So I'll just zoom out. Yes. Now again I have a question which says, what is the probability standard box weighs more than 350 kg? So 0.350 kg, sorry. So that means that I have something like this and I have a normal distribution. and this is my mean, and this is my random variable. So this is my mean, and this is my random variable x. I have some SD, right? Now the direction of the progression is where? On this side. And I don't need to find the area under the curve on this side. I have to find area under the curve on this side. Okay, it is in line with the progression. It means it is not cumulative. So what do I do? In that case, what can I do? Let me just clear all the drawings and let me come over here. Can I calculate the Z value? The answer is yes. I have all the requisites or all the prerequisites to calculate the Z value. Let me calculate 0.350 minus 0.295. This divided by 0.025. Right? This is going to be my Z value. Is this correctly done? Let me cross check. 0.350, 0.350, 0.295 is the mean, good, and standard deviation 0.025, right? Now, obviously, as I have already explained you, the Z value is going to be a positive value. So what do I do if it is a positive value? I can either use this function to calculate the probability, or I can use another function. Okay, let me use this function and see what is going to happen. Is equal to norm.dist. Okay, then I'm going to put the value of x 0.35. Then I'm going to put the value of mean 0.295. Then I'm going to put the value of standard deviation 0.025. Then if I put a cumulative distribution equal to true, this value that comes is the opposite value. This is not the correct value. Ideal condition, I should have put this equal to this, right? But see what is happening here. The way Excel calculates it, okay, is by giving preference to cumulative. Hence, what trick that we are going to use, and this may be applicable on Python as well. Okay, so the trick is to find the opposite. So what I am doing over here is, this is the graph. This is the mu, very bad drawing. This is x, and I want to find this. So rather than finding that, what I'm finding instead is this. I'm going to find the area under the curve on the opposite side using a cumulative value equal to 1, right? I'm going to set the flag equal to 1 and I'm going to print 1. If I do that, then how do I calculate this one? I do a 1 minus. Why am I doing a 1 minus? I'm assuming in this case that it is going to exactly fit by 1 minus. In the earlier case, when I told you that this is 27.46, does not mean that the rest is 1 minus this value. Okay, does not always mean, but in this case, we will simply assume that. That is one way of doing. Okay, it is all a probabilistic game, so there is nothing wrong in doing any assumption here. Why? Because we are limited by the function. And because the function is confined or inclined towards the cumulative valueness, so that is the reason why we are going to use the other function or the other way of using the function. Okay, so in this case, what do? I simply click on this once more and I say 1 minus. I get this, and then I do again the same thing. I take this value, multiply this by 100, round it to 2. I get a 1.39. What if I again say that I want to calculate the probability using this norm.dist function in a different way? Let's say norm.dist. I'm going to put 0.35, 0.295, then I have 0.025, and then I have 0. If I put this, 1.41 is approximately equal to 1.39. This is exactly what I wanted to show you, right? This is the inclination effect. This is the inclination effect of a normal distribution. In this case, it should have ideally given me a value between 0 and 1. That is the probability value, right? It can never exceed 1. But what it has done is it has given me a value which is quite close to the actual percentage probability value. So multiplied by 100. I have no idea if this is going to be multiplied by 100 or something else. Okay, why is this the case? Because of the inclination, because of the cumulativeness. And that is the reason why we are not going to do this. Right? We are not going to do that. We are going to do with the traditional method. And here we find that the probability of a standard box, if I pick up from the store, weighing more than 350 grams of raw cereals within that box is going to be only 1.39%. Right? Now, am I going to say that there is This multiplied by 100, 2. Is this the percentage probability that all the boxes weighs less than 350 gram? The answer is yes, if I am assuming that all the objects or all the assumptions or all the other assumptions or the setup of the experiment is stationary. Okay, what I mean by that is I'm absolutely confident there is no confounding variable. Nobody is doing any such activity in the machinery or in the experiments, in the events that I'm doing, in the data that I'm actually collecting over here. Nobody is doing any such kind of interference, and that is why I can safely assume it is 1 minus. That is the only case in which I will assume. Otherwise, it may not be 1 minus this value. That is not always the case, as I've told you in this case as well. Just because it is 27.43% doesn't mean the rest 72% is on the other side of the river, right? So that's not going to be the case. This is also not going to be the case. But you may want to use it by assuming that there is no effect of no confounding variable, right? So you have to specifically mention. Why I'm saying this is because when you are going to tomorrow present your analysis, you have to mention these. You have to specifically mention these when you are articulating your findings. When you share your findings, don't simply say, I am 100% confident there is a 1.39 percentage of a probability that a standard box weighs more than 350 gram. There is nothing called 100% chance. At a certain point in time, after a certain point in time, we will come to know that as a statistician, we can only be sure up to 95% of time. And that is otherwise known as a confidence interval. I don't want to go into there right now because we still have to look at some other things first of all. But there can nothing or there can nowhere be a situation where somebody says, I'm 100% confident. So next time you see somebody talking like that, you should stop that person and tell him or her that there is nothing like 100% by data. Okay, by numbers, 100% is impossible. Why? Because we already know 0 and 1. These are the extreme ends of the probability. They are almost not applicable in the real life scenarios, right? In the same way, I cannot do a 1 minus and say that I'm 100% sure that 98.61% of all the standard boxes are going to weigh less than 0.350, right? So that is the reason why I'm going to delete this portion. I'm not going to use it. Okay, but if you are going to use that, please mark that with an asterisk, and at the end of the document, please take a footer and please mention that into your analysis, into your finding. If you are going to present it as a PPT or a PDF or a Word doc, please clearly mention that. Any doubts until now?
Yeah, hello.
Yeah, hi Rohit, go ahead.
Yeah, actually, I'm not able to understand the last variable when we have to use one and when we have to use zero. Can you please clear on that?
Okay, this one, right? So see, norm.dist is the function where we are trying to simply figure out uh, the normal distribution, although the name says that, but we are simply trying to figure out the probability using the PDF. So we are using the probability density function. We already have a graph with, oh no, I'm sorry, let me choose another. So I have a graph like this. I have something like this. So this line is actually a PDF. Now using this PDF, I'm going to take any random variable which is falling on this horizontal axis. Let's say this one. And then if I draw a straight line, I'm going to take an area under the curve over this side. Okay, let's say my question is something like this. Why? Because my data progression is on this side. From small to high, this is what I'm going to do. If this is the case, okay, if this is the case, then ideal condition, I put the cumulative value is equal to true if it is a cumulative distribution function, or I put it equal to 0 if it returns a probability density function. Now this is going to be more confusing than the previous thing, but let me clarify. My point is, can this normal distribution be converted into a cumulative distribution like this? The answer is yes. Why? Because it has all the properties of a normal distribution. It does not simply look like one. It is actually one. So mathematically, you can prove that this PDF can actually be converted into a CDF, and then it is going to look like this. And that is the only reason why, because of this finding that this is a properly normally distributed variable, or a random variable x in this case is really a normal variable basis the tests that we have done yesterday as well, right? So basis the tests that we have done, we are almost sure, we are near to 100% sure this is a normal distribution. Every normal distribution is going to have a CDF, and that CDF is going to be like this. So it is going to be a very smooth kind of a curve. If that is the case, then I'm going to use that last value is equal to 1. Else I'm going to use the last value is equal to 0, or I can use true, or I can use false, right? Many of the cases, this is what I'm going to use, right? What is the reason why I'm going to use this? Because ideal condition, if you've already figured out that this distribution is actually normal, then it must have a CDF, and hence Excel prefers using this. And that is the reason why in industry we seldom use this. We use this and do the manipulation. So example given, let's say I have my graph which is something like this. I had my mean over here, I had my random variable here. I needed to find this, right? But instead what I did is that I found the other side. I found the value for the other side, and then I simply assumed that there is no confounding variable. Hence I did a 1 minus p, and I found out this, right? Because this becomes 1 minus p if I assume there is no affecting variable. So that's exactly the point. I have one when I can convert a PDF, or this PDF can result into a CDF, which I'm 100% sure, because I know that this is going to act as a cumulative. Why? Because this is the direction. And if I add the probability of the random variable x1 and let's say x2, it's going to give me one value that corresponds to the probability of x2. Because of this cumulative nature, my value for this graph should always be equal to 1. Else, if I have any doubts that this is only the probability density function of any, let's say, random data distribution, which looks like a normal distribution, it may not be, then I'm going to use 0. Okay, but the chance is very, very less. Did it clear your doubt?
Yes, yeah, thanks.
Okay. Yeah, I know we have not really covered the calculus part. We don't need to. This would have been more clear if we would have been covering the calculus part. I deliberately don't want to cover that in depth, because that is only going to confuse you. There is hardly any need of learning, let's say, calculus in all of the machine learning. There are only few areas like area under the curve when we are going to, let's say, look into use cases like whether this email is a spam or a ham, or whether a person who was traveling into Titanic ship is going to die, or he or she is going to survive. Then such kind of classification algorithms is where we use a metric. We are going to discuss that in breadth when we are going to look into machine learning. So there are certain measurements by means of which we decide whether the modeling that we have done is really good or it is not good. In that case, we come under, or we come towards, this is just an example, by the way. There are other machine learning cases as well where some bits and pieces of calculus is used, but we don't really need to be an expert in calculus. Even I'm not. I just understand what is area under the curve, and I understand what is, let's say, gradient descent. So we are going to use them when we do machine learning. We will come to know what these are. Answer 3. This is the most interesting answer of today. I think we can answer this question and make a stop, because there will be, I expect there will be questions. Because in this case, I'm not going to have only one Z value, I'm going to have two Z values. Okay. Why am I going to have two Z values is something I'm going to answer, and then I'm going to give you the probability. Okay. This probability basically will be really, really interesting to calculate. Okay. Now, why do I have two values over here? Is that I have, or why do we have two values of Z over here is because, let me again draw. So, okay. This line is, sorry, this is a straight line. This is the x, right? So this is my random variable x, and this is my normal distribution. I have a mean over here, which is mu. Okay, this mu is equal to 0.295. What is the question? There are two random variables, 0.260 and 0.340. One which is less than mu, one which is greater than mu. That means it is asking us to find the probability of a range of values. Right? It is asking us to find the probability of a range of values. Right? If it is asking for a range, then what we need to do, keeping in mind the cumulative nature, we have x1 and we have x2. Calculate the z until x1. Give it a name z1. Just like I have given it a name, z value 1. Right? So I get the z value for the first. So up to 1 point. Okay, up to 1 point I get the value. Okay, then I get up to the other value. Right? I get the z for up to the other value. Let's say this is z2. For each z, I can calculate the probability. Right? I know how to calculate the probability very easy. I can use the norm.dist. Because this is a normal distribution, I can use the norm.dist. Right? And then I can find out, let's say P1, which is the probability basis score Z1 or value Z1. And then I find out probability P2, which is basis the value Z2. How do I find the range? I take P2 and I minus P1. Why? P2 or P1 is this part. Right? And what is P2? P2 is the entire part. Right? So I need to find the intersection. If I have to find the intersection, the overlapping part has to go. We have already seen this in the multiplication rule. We have to get rid of the intersection part. So this part has to go away. I just need the value until this point. If that is the case, I get P2, which is this. I get P1, which is this. I simply minus P1 from P2, and I get the remaining. Right. So this is exactly what we are going to do over here, and then we are going to find out the value. So this is probability. I'm not going to write this probability. Probability 1. Right. So let me just increase this value, and then I'll say probability #2. So #2 represents the two values. So what is the z value of the first case? First case, you can take any one. Okay, it is not really a problem whether you are defining x1 or x2 or x2 or x1. You just have to subtract the one for this from this. Okay, so let me take z1 as this. Okay, let me take z1. This corresponds to 0.340 kg. And z2 is going to correspond to, let's say, 0.260 kg. If I'm going to do that, then final probability, the final answer is going to be what? This minus this, the probability that I get over here minus this, right? So probability 1 minus probability 2. If I would have taken the opposite value, you can take anything. That is not an issue. You're simply finding a real number without any scale, right? You would have taken the opposite one. You would have said, I have taken 0.260 here. 0.260 is that? Okay. 0.260 kg here. So if you would have taken 0.260 kg here, then you would have said it is P2 minus P1. So you simply manage the calculation in that way. But you just have to remember basis the diagrammatic representation. So you must always have a rough copy to draw something like this, or try to visualize this. If this is Z1 and this is Z2, or for the point x2 I find z2, for z2 I find p2, for the point x1 I find z1, and for this point I find p1. Then I simply minus p1 from p2. Why? Because p2 is the higher value. In this case, you see my p2 is the lower value, right? So that is why I'm doing it the opposite way. So let's try to find out this, and then we can close for today. So we will find this 0.340 minus 0.295 divided by 0.025. This is the value. Okay, 1.8. And then I have another value. which is what? 0.260 minus 0.295, bracket closed. Then I have 0.025. Right now, what is the probability of this and what is the probability of that is what we need to figure out. Right, so let's calculate the probability. We know we can use this norm dist. Okay, but I'm not going to use that. I'm going to show you something else. I'm going to show you norm.s.dist. In this case, I don't need to put all the values. I just need to put the z value. In this case, what is my z value? 1.8. And then I put cumulative is equal to 1. Okay, this is 96.41 approximately, you can say. So this is like 96.41 approximately, right? What about this norm.s.dist? Again, I take the z value, which is minus 1.4, and I say this is 1. Right? If I do that, then I get this. This is what? Is this the right thing that I have done? 0.80. Yes, this is the right thing. Yes. So this comes up what? 8%, right? This is approximately. Yes. Why to take a risk? Let me just calculate this. 100 scale 2. Go ahead. 8.08. Let me just copy this and put it over here. So it should give me 96.41 using C19, and this is this. Okay, so my final answer, this is not my answer. Huh? My final answer is this. P1 minus P2, I said. P1 minus P2. 88.33 is the probability that the boxes falls under the weight range of 260 grams until 340 grams. I calculated two Z values. One for upper bound, one for lower bound. I can name them P1, P2 or P2, P1. It does not matter. What matters is the concept. Concept, I have the Z value. I calculated the probability. Earlier, I calculated the probability using norm.dist. This time I did something else, hence I'm going to write it over here. This is norm.s.dist. Sorry. This is norm.s.dist. And then I'm going to say, here, I don't have all this mu, SD, RV and all those. Put the Z value. Simply put the Z value and then you give 1, 0. Please mind, we could have done that here also. I just wanted to show you the use of Z value and another function. That's why I use this. Or otherwise, norm.s.dist is going to apply here. I simply use this function, get the probabilities. Okay. Then the basis my diagrammatic representation and cumulativeness, I simply do this calculation. I get the answer. My job is done. Right? Is this clear or are there any doubts?
Yeah, so the answer will be same if we will use norm.dist for this.
Yeah, because you see what you are doing over here is that you are using 1.8 over here, right? So why not try this? Yeah, so 0.36, 0.295, 0.025, 1. Right? You get approximately the same number. No, this is not the same number. What kind of a mistake did I do? 0.025 only, right? I did the same. Okay, I think. Oh, no. Sorry. This is 3, 4. Yeah. So now I get a value which is this. So this is for the first value. Let me just cut this and put this over. And then for this one, I don't want to use norm.s.dist. I'll use something else. So norm.dist, and then I put 0.26, right? Last time I made a mistake. So 26, 0.295, then 0.025 and 1. See, the answer is exactly the same. No matter what you do, you're simply replacing those three values with one value. Then you do the calculation.
Okay. Okay, and what is this S? What is the full form of S here?
I don't know that. I'll have to check that. I'll have to check. Let me just quickly Google and check. Norm.s.dist. Norm dot s dot dist. Standard normal distribution. That S defines a standard, which has a mean of 0, standard deviation of 1. So,
Okay,
Sarangs
okay.
is raising hand. Maybe Sarangs, you can ask your question. We have less than a minute.
Okay, Bhawmik, so let's say for answer 1, we have some probability, and answer 2, we have some probability. And for third answer, we want to find the probability in between,
Hmm.
right?
Hmm.
So in the end, the probability is actually some 100%, right? So at